there. All right, so as I said, this is the battery, right? Here. This is your wire, the pink looking material here. That will be your wire. Let me respond to this person in the group. The meeting.
There is the pink thing showing what's inside of the battery.
No, this is the, you know, like your battery. You have two sides. You have the positive side and the negative side.
Yes, sir.
You would connect wires to that battery. So the pink thing would be the wires, like regular wires that you'd find in toy cars and so.
Awesome.
All right, group description. Right. So if we increase, say we increase the power of the, let me see. Yeah, like a copper wire. Exactly. Now, if we increase the power being pushed out by the battery, so say we increase the voltage on the battery, what happens to these blue things? Right? What happens to them?
They increase, they get bigger.
All right, so not really bigger. Let's try that again. What happens to the speed that they're moving at?
It increases.
Exactly,
Faster.
so it increases. So let's bring it back onto 2.88. Right, so they're moving at this steady all right, so they're moving at this steady speed, and these are what can we call these blue things? What do you think they're called?
Electrons.
All right, so they're called electrons, and they essentially carry electricity, right?
Yes, sir.
So electrons, thank you for that, carry electricity, and they essentially represent the flow of charges and how charges move. Now we see that the battery pushes out voltage, right, and current, and this essentially interacts with this right here. This would be a resistor, right? This should be a resistor, or it could be a light. It could be a light bulb, right? It could be your phone. So these electrons interact with the particles or the charges inside of the resistor, right? And essentially, it will cause them to get power. All right. So as we said, if we increase the voltage up to 5 volts, we see that there's an increase inside the flow of charge. And look on the bar down here, right? The object gets what? What happens if we increase the voltage?
It's good.
It heats up due to the friction of the movement.
Exactly. So it increases because of the flow of charges. All right. Now look on, remember this over here? We spoke about this in the first class, right? This amps here, right? We spoke about this, remember? This is used to measure, right, the flow of charges. All right. So if you look on this and we increase the voltage again, let's look on this again and we increase the voltage. It's at approximately 9. So this is 0, 10, 20, 30, 40, 50. This is about 9, right? So if we increase this, what happens to the reading on this meter?
It moves to 20, sir.
All right, so it moves to approximately 20, right? Yeah, so it moves to approximately 20. And we see that these are actually moving much quicker than they were moving before. So that's what we want to accomplish for this particular exercise, right? Before we go into the actual notes. I'm bring it up now. All right, so let me know if you're seeing this.
Good morning, sir.
Yes, sir.
Yes, good morning. All right, so let's begin. So yeah, we want to formulate a simple working definition for the term electric current. We want to classify materials or substances as insulators and conductors of electricity. Construct simple circuit using lamps, insulated wires. Remember we saw wires, right? We saw the pink, and we said that the red thing at the top could represent a lamp, right? And the wires and dry cells would be your battery. That's what we call batteries, dry cells. So if you ever see dry cells, right, anywhere, right, that means battery. All right, that is just a scientific term for battery. Please make a note of that, right? So you might see that popping up again somewhere. All right, so switches to distinguish between series and parallel circuits. We'll probably do this next class. All right, but we want to try and complete the first two objectives today. All right, so electricity. Electricity can produce light, heat, and sound when flowing through a circuit. All right, so we saw when the electric charges are moving, right, through the wires to the resistance, to the resistor, which was the red material, right? That's how electricity moves. And as we said that when we increase the voltage, what happened to it? Did it get hotter or colder again?
It gets hotter, sir.
Right? So it got hotter, so that means that electricity was flowing through it with a lot more power. Therefore, the device got hotter. So electric current flows to a TV. Both sound and light are produced. So it really depends on the type of mechanism that you will have, right? That will, so if you apply electricity to a light, it will have a different purpose if you applied it to a computer or a printer. All right. So it really depends on the type of machine that you're producing the electricity to, or you're delivering electricity to. All right. So electric current flows to a toaster. The heating element, right? Remember, we say as we increase the electricity or the electric charge, it got hotter. So this can be applied to a toaster. So the heating element wires, they get hot enough to turn bread a toasty brown. All right. So electricity flows in a closed path, as we saw when we moved from this side of the the battery, going down this side and going back around, right? Going through the resistor. Remember, this was the resistor here. This red thing. This was your resistor, right? Remember?
Yes, sir.
And so the light will represent the resistor, all right? And electrons flow back through the battery. All right, so that's how it really goes. So closed circuit, electrons can flow and the light bulb shines, right? What happens over here? What is happening in the open circuit? Is there any light?
No, it doesn't shine.
Exactly. So
over here, sir.
Because this is not connected, right? So this,
Yes,
Yes.
yeah, electrons can't flow,
Yes,
and therefore the light bulb doesn't
It's
shine,
like
It
blocking
wouldn't
the
be
flow
bright,
forever.
sir.
right? I heard something.
Sir,
It's like blocking the flow forever.
All right, so it's blocking the flow forever, and I heard someone else. I believe
Wouldn't be bright, sir. The light wouldn't be bright.
All right,
Not as
so
much as want.
right, so the light wouldn't come on at all because there will be no electricity flowing through it. There will be a little space here. It's called an open circuit. All right, so electricity flows a closed path to form a circuit and stops when the circuit is broken. So if there's a broken circuit here, if you have a toy that produces light and one of the wires is broken, you find that the toy stops working and you would try and throw it away. But essentially what you should do instead of throwing it away or just abandoning that toy, you can open the toy and look where there's a breakage in the electricity, right? Look which wire is broken, right? And then you can highlight that wire and connect them back, tape it, and then your toy will be good again, right? So usually we classify materials as either conductors or insulators. So conductors are copper, aluminum, and steel. Right? These are the materials that we mainly use to conduct electricity. Copper, aluminum, and steel. Right? You'll find copper mostly in wires, right? Because they are so they have a lot of conductive material, right? And they are good conductors of electricity, right? And they provide little resistance to electric flow. So they're good for wires, long distance electricity. Right. So if you want to power, say you're in Kingston and you're at a power plant at JPS, you would more than likely, if you want to send electricity to Ocho or Trelawney, you use copper because it is a good conductor, mostly copper. But all of these are also insulators. No copper conductors, sorry. So what are some insulators? Give me some examples of insulators that you may know. What are some insulators?
Plastic.
All right, so plastic, we hear the word plastic. That's good. Anything else?
Rubber.
Rubber, right?
Glass
Wood.
and wood.
Glass and wood, right? So anything else I'm missing out?
Paper.
Paper,
Glass.
right?
Cloth.
And cloth, right?
Yeah, yeah.
Okay. So you can therefore identify which of these are conductors or insulators. So let's look on the coin. Is the conductor or insulator?
Conductor.
All right, so this is a conductor. I am not sure what this is. What does this look like? Paper, right?
Paper.
Right, so as you said, this is an insulator, and this is a...
So all of them are labeled.
Again? They're labeled, but the resolution is a little poor, right? We can skip this one. I'm not sure what this is. This one, what does this
It's
look?
a champagne glass opener.
Yeah, it's a champagne glass opener. So what I mean is that I'm not sure if they're talking about this section or this section. I'm not sure which section are they talking about. But let's look at, all right, let's call this A and we call this B. So which one is the conductor?
B.
Right? And which one is the insulator?
A.
Yeah.
A.
All right. Next one. Would the gloves conductor or insulator?
Insulator.
And the wood at the top here?
Insulator.
Insulator.
And what does this look like? Is it like wool again? Wool, right? Of a sheep.
Sheep.
Insulators.
So insulator and trumpet.
Conductor.
Conductor, right? And the leaf here, of course.
Insulator.
The brick wall.
Insulator.
And the ring. What's the ring?
A conductor.
I'm not sure what this is. Oh, soda can. The soda can.
A conductor.
Alright, and this is a styrofoam cup.
Insulator.
Plate and
Insulator.
spoon.
Insulator.
Frying pan.
Insulator.
Frying pan.
Conductor.
Right?
Conductor.
So we find that some frying pans will be made of aluminum or steel, right? Tire here.
It depends on which part, sir.
Right? That's good. So what about this part here in the center?
A conductor.
Conductor.
And then outside would be
An insulator.
right. And the last one is a little tricky, right? Well, let's look at the thermos, right? The thermos is a what?
Conductor.
Conductor, sir.
It's a conductor, right? But then you will have some parts on your thermos that
That is insulator.
right? Yeah.
Integrate.
Why? Why I think there are some parts on it that are insulators? Why is that? What's the purpose of the thermos?
To keep heat or
Exactly.
cold.
So you have some parts on it that are insulators, right? You would have some steel, and you have some parts that are on it that are conductors, such as steel and so forth. But then it is essentially designed as an insulator to keep hot things hot and cold things cold.
Cold things cold.
Right. So insulators. So to insulate, let me answer this student. They will be posted. All right. So insulators, they essentially insulate energy, right? And this means to prevent the transfer of energy. So it don't allow heat or electricity to pass. That's the definition of insulators. They don't allow heat or electricity to pass. And as I said, these are some examples of insulators. Rubber insulates electricity, right? Air insulates heat, and wooden spoons insulate heat as well, right? So say you have a spoon and you want to remove something out of the pot, you'll find that you would use a wooden spoon, which would
yes, sir.
Yeah, so
Sir,
a
it's
wooden
like if
spoon
you
is
leave a metal spoon and a wooden spoon in a pot, sir.
yeah, exactly. Or sometimes I mistakenly leave my spoon on top of the pot while it's cooking on the pot cover, and when I go back, I cannot do anything. I just have to use something else, right? Or find something. But if you had a wooden spoon on the other hand, you would be able to make
use
it.
it.
Yeah, right. Essentially. All right. So the conductors.
Anything.
So conductors now, to conduct energy means to transfer energy on the other hand. So we see insulators and conductors have their purposes. They have their, different purposes, their different reasons for, So
Yes, sir.
conductors allow heat or electricity to pass from the object. So we have metal wires conduct electricity, metal pot conducts heat, and metal spoon conducts heat as well. Right. All right. So the electric current now, we move to electric current, and it is measured in amps. Right. Do you remember this picture? Right. This looks very familiar.
Yes, miss. Yes, sir.
Right. This picture looks very familiar. We saw this on our first test. Right. We saw this on our first test. And remember the name of it? Do we remember the name? Right, the MA here, right? So we need to go back and look it over again, just in case it pops up on your test. So it's called an ammeter, right? And what is it used to measure?
Where measure again? Electricity.
Right, electric current, right?
Yeah.
Yeah, so the ammeter is essentially used to measure electric current, and it is measured in amps, right? Or
the
in this
voltage.
case, all right, so that's another problem right there, because you have a difference. Let me see if I can find that slide quickly. Just to not cause any confusion, I will keep that and go here. Let me bring up that slide quickly before the time runs out. I'm just using the first session, so when the Zoom call ends here, that will be it for today. All right, we can continue next week. We'll bring over the objectives for next week. Where is it? Okay, here. All right, so I'm gonna bring this up. Where is this one? All right, do you remember this now? This look familiar now, right?
Yes, sir.
Right, so we have one with MA, one with MA here, and one with V.
Yep.
Right, so the MA is signifying your ammeter, while your V is signifying your voltmeter.
Voltage, yes.
Exactly. So we don't want to mix them up, right? It's going to pop up again. As you might have already been aware, I will find the smallest detail, right, and make it a custard. So you have an ammeter here, is used to measure current, and voltmeter is used to measure voltage.
Voltage.
All right, so good. Are we all clear on that?
One.
So what's the difference between amps and voltage?
Right, that's what we'll discuss now. We'll talk more about that now. So keep, close, save. Screen.
There, I think Does voltage measure how many?
So go ahead. Voltage measures how many?
Volt, sir.
Is
That's a good.
coming is giving out her. I don't know.
All right. Okay. Now as I said, let's just finish this up. Electric current is measured in amps using an ammeter connected in series in the circuit. Right, we have our ammeter here. This is a digital multimeter. You can use this to measure both of them, right? So this is the newer types of ammeter. You can use this to measure. You won't have to have one for amps and one for voltage. You can use this one to measure both, right? So this is called a multimeter, right? So you can measure multiple things, right? So you can measure both amps or current. Get rid of this. It can measure both current and voltage. So when you're doing physics, right, before you started doing physics, you hear people mixing up the term current and voltage, right? And you think they are essentially the same. And there's a lot of other things in physics that people really mess up, or they don't fully understand, so therefore they just make an assumption that they're the same, right? But in physics, you get a lot more understanding. So how you should be thinking about electric current. So electric current, as you saw in the initial experiment, right? We had a battery here. We had a battery here in the initial experiment, and it went around to a resistor, right? This is a resistor. This is like your lamp. Say, for example, this is a lamp. All right. Now, the electric current, when measuring electric current, we measured how much, right? How much charges or how fast the charges were flowing. So whenever we're measuring electric current, it is a signal of how much charges are flowing or how fast they are going. So look at the river here. The river is flowing in this direction. If the river starts to flow much faster, then it will have a higher current, right? You hear people talk about current in water, right? This is essentially what they mean, the flowing of the river. So as the river begins to flow much faster, or there's more rain, right? Then you'll find out that it has more current, right? Voltage, on the other hand, right, we're not going to go too deep into it, right? I'll speak to my supervisor and ask if we can include voltage, but we're just required to know about current. But let's talk about voltage for a second. So voltage, right, is that pressure that the battery puts out. So we realize that when we increase the voltage on the battery from 2.8 to 4, right, when we increased it, we saw that there was an increase in the flow. So the battery provides a pressure that pushes the electrons that will cause them to move much faster. That is the definition of voltage, right? So is that pressure that the battery pushes on it. All right, so let's go back to that quickly again to ensure that everyone is clear. Right, so let's bring this back down to, it was at 2.88. It started at 2.88. Right, now we look on this speed. Look how fast these are moving. Just look how fast they're going. Now, when we provide more pressure, or more voltage, we see that there's a slight increase in the amount of
Yes,
charges
sir.
that are moving. So we see that there's an increase in the flow of charges. They are moving much faster, and our object
Yes.
is essentially getting hotter.
More electrons coming out, sir.
Exactly. So there's more pressure being pushed. So essentially, the voltmeter would measure that pressure, while the ammeter would measure how fast the electrons are going. All right. So
And
is that
both the
clear?
battery and the resistance will be hot, sir.
Exactly. Exactly. All right. So that's why when you're running games on the phone, right, the battery has to provide more pressure or more
Yes.
power, and then essentially it gets hotter. All right. Is that clear for everyone now?
Yes, sir.
All right. Right. So as I said, it's electric current is represented by the flow of a river, right? Let's see if we can. So you would have the small droplets. They would represent the. What would they represent? The small droplets. These droplets here, what would they represent from our experiment a while ago? See them? Are you hearing me?
Yes, sir.
Yeah, what would
Electrons.
these, yeah, so these would represent electrons perfectly, right? So small electrons, these represent small electrons. So on the river, you could measure how fast the river is flowing. That would represent the current. All right, so current, the actual substance that is flowing through the wires of the circuit are called electrons. So the actual substance. And we measure how the rate at which they are flowing through through current. Let me see here. All right, so we can move on now to the circuit. We can start looking at circuits, right?
Yes.
So let's bring this up back again. We have a battery here, or as I said, battery or dry cell.
Yes.
Or dry cell. And it goes towards the switch. With this switch, right, the switch here, this is a symbol for it. We can turn off or turn off the light, right?
Yes, sir.
Yeah, by essentially blocking the power being driven to our light here. So we can turn it on and off, and we can turn it on and off. So the symbol for the cell, let's draw this before the thing comes up, right? So we put our cell here. Then next, what will we have? What's the next thing?
The switch.
Right? So then we put our switch here.
Oh.
Right?
Yes, sir.
The wires, of course, looks like this.
Yes.
I probably should change the color of the pen. Probably. Let me see. White.
Yes, sir. Right.
Let's try it again. Do I have a battery? Go over here. We have our switch.
Yes.
Then what's next?
The lamp. The wire.
The lamp. So the lamp looks like this. So this would be your lamp here.
Yes, sir.
And then we come back around and we finish the circuit. So the circuit is finished, right?
Yes, sir. Yes, sir.
Yes? Look on it again.
No, sir. It's an open circuit.
All right, so this is an open circuit. So we have to close it. So we have to connect back. So this represents our battery or our cell. There's a small space in between, right? And
Yes.
this represents our circuit. So let me just take this off. Let me see if it comes up. All right, so that's a much better picture. So let me take off my ugly picture here. So it's essentially the same thing, right? If the switch is over this side or this side, doesn't really matter. Once the switch is connected to the circuit, it should be okay. All right, so are we all clear so far?
Yes, sir. Very clear. Understanding.
Yes, sir.
All right.
Yes, sir.
Okay, good, good.
I'm subscribed,
Morgan,
sir.
are we good?
Yes, sir.
All right, good, good, good. I think we can end here for today. Next week we will start series on parallel circuits, so we can, let me see. Yeah, let's start series on parallel circuit next week and then do a small recap. All right, so all the best, everyone.
Same to you, sir. Have a good day.
Yes, sir. Have a good day.
Are you yarning in the mic?
Yes, sir. He was.
I'll just pretend that did not happen. All right. All right, all the best.
Same to you.